Okay, let's work 2.13. Find a basis for the row space of a given matrix, a 3x4 matrix. At this stage, we haven't dealt with bases for row spaces in much detail. We'll deal with that in the next section. So let's take a look at the notes from section 2.1. We do have a way to find bases. It's effectively bases for column spaces. But in theorem 2.1.a, finding a basis for the span of a set of vectors, what we do is put those vectors in a matrix as columns, row reduce the matrix to a row echelon form H, and then pick columns of matrix A that are in positions corresponding to pivot containing columns of H. So, we got a little problem here. A row space is a span of the rows of matrix A. So we want a basis for the row space. We want a basis for the span of the rows. 1, 3, 5, 7, 2, 0, 4, 2, and 3, 2, 8, 7. So if we translate it into a question about a basis for the span of a set of vectors, then we can use theorem 2.1.a. Based on by theorem 2.1.a, we consider a matrix that has these three vectors as its columns. Theorem 2.1.a required vectors and columns. So we take 1, 3, 5, 7 as the first column, 2, 0, 4, 2 is the second column, and 3, 2, 8, 7 as the third column. We'll row reduce that. We'll find a row echelon equivalent form of this. We'll call that matrix H, and from there we can find a basis for the span. Of course, we'll have to translate all this stuff back into terms of the original question, which was a question about a row space. So I tell you what, let's let Wolfram alpha do the row reduction. So we need to run to Wolfram alpha. We can access it through, say, the syllabus. So if we'll go to Spring 2020 version of the syllabus, all my syllabi look alike for this class, and we'll scroll down, you'll find a link to Wolfram alpha. We'll go there, and we want to row reduce, actually reduced row echelon form, the given matrix. So the syntax, really elementary in Wolfram alpha, RREF for reduced row echelon form, then a set bracket, then we'll enter the rows of the given matrix because that's Wolfram alpha's syntax. So carefully enter those. It'll give us a pretty display of what we've entered. It'll tell us if we violated the format too. Okay, let's see what we get from that. Oops. Okay, it asks us to verify really what we've entered, and that is correct. And it gives out the row reduced echelon form given here. So that's what we get. So I'll translate that over to the board. So for matrix H, we have first column 1, 0, 0, 0. Second column 0, 1, 0, 0. So that lets us pick out our pivots. Third column was 2/3, 7, 6, 0, 0. Okay, so we found pivots in the first two columns. Theorem 2.1.a tells us if the first two columns of H contain pivots, then a basis for this set with which we were dealing has as a basis the first two vectors. So, by theorem 2.1.a, a basis is given by the first two vectors in the spanning set okay, so that'd be these two vectors here, but these are written as row vectors. They went into the matrix as column vectors. Technically, theorem 2.1.a tells us to take these two columns, but correspondingly, we get the first two vectors. No matter if you slice it, we get those two vectors. And hence, a basis for the row space of matrix A is, and we'll express it as rows, since that's the setting. First two rows, 1, 3, 5, 7 as a vector, and 2, 0, 4, 2 as a vector. There's a basis. That's what we're asked to find. So there's the final solution. And you might notice something about the matrix we considered over here. We actually found, it's a little free education here, we found a basis for a column space of not matrix A itself, but actually A transpose. But the column space of A transpose is the row space of A because the columns of A are the rows of A transpose. The columns of A transpose are the rows of A.
Oh, well, here's a Band-Aid.
And on.